In this second part, we will talk about Birkhoff sections on suspension and Anosov flows and its relation with some particular family of singular affine structures on surfaces. Let's start by recalling what's a suspension Anosov flow. So we consider a hyperbolic matrix, a 2 by 2 matrix with integer coefficients and trace greater or equal than 3. Um, so it has two eigenvalues of modulus different from 1, and let's call Fa the linear automorphism induced on the two-dimensional torus by this matrix. So here the two-dimensional torus is the quotient of the plane R2 by the integer lattice cell2. And this linear automorphism is an Anosov diffeomorphism in particular. Consider the manifold T2 times R and this flow acting on it, and consider the transformation tau, which sends a point xs. Well, this is a translation by one unity on the R coordinate, so here we have s minus 1, and in the t2 coordinate we apply the Anosov diffeomorphism Fa. Okay, so when we quotient t2 times R by this homeomorphism tau, we obtain a three manifold that we will call MA with an induced flow. This is the suspension flow generated by the matrix A. Of course, we will be interested in flows up to orbital equivalence, so we call a suspension flow any flow that it's orbitally equivalent to this one. Okay, and as we remarked in the first part, suspension Anosov flows are the simplest Anosov flows for many reasons. In particular, they are the only ones who has a global transverse section, and the fundamental group of the three manifold MA is solvable. We are interested in the following characterization of suspension Anosov flows. Um, this characterization um, comes back to Plant, but the works of Plant, but with many contributions of Thierry Barbeau, and says the following: an Anosov flow in dimension 3 is orbitally equivalent with a suspension Anosov flow if and only if there exists an associated transverse affine structure. And what's a transverse affine structure? Is the following. It is an atlas A um, of maps phi, which are embeddings of two-dimensional disks contained in the plane inside the three manifold, such that each of these disks is embedded in a transverse manner. So it is transverse to the flow lines, embedding is transverse, like in this figure. And consider some point, consider a point in one of these disks, like this point here, and assume that the future iteration by the flow of this point hits another disk, like in this picture. By the continuity of the flow, there exists some open neighborhood of this first point that is mapped projected by flow lines onto an open neighborhood of the hitting point here. This map A map like this is called a projection along the flow or a phi projection from one disk to the other one. And we will require that if we pull back the homeomorphism PIG by using the charts of the atlas, so we obtain another homeomorphism, but now in the plane here. Well, we will require that this homeomorphism is an affine transformation of the plane. And third, we will require that there exists some positive time t such that any orbit of any orbit segment of length t intersects the union of these disks. Well, coming back to the planned Barbeau characterization of suspension and also flow, if we are given some suspension, consider a global transfer section that here in this figure is represented by T2 times 0. And consider the universal cover. Well, this torus is endowed with a natural translation structures. This is an atlas where coordinate changes are translations, and it's produced just by the quotient operation in the universal cover. So in particular, this is transverse affine structure for the suspension flow. And the change of coordinates are translations. And we can produce another affine atlas. Maybe it's a little more artificial, but it is as follows. Consider charts of the translation atlas, which are homeomorphisms from open sets in R2 inside the global section. And then we will compose these maps with some iterations, with some power of the Anosov diffeomorphism Fa on the torus. Okay, well, so this set of homeomorphisms produced in this way, it is also an affine atlas, a transverse affine atlas. But it's not a translation atlas. We have introduced another kind of transformations which are of this form. Let's remark now some facts of Birkhoff sections on suspensions. We start we start with some example that is due to Minakawa. So we consider the torus and the matrix A given by 0, 1, minus 1, 3. This is a hyperbolic matrix acting on the torus. And for this matrix, it is possible to find an orbit of period 2, which are these 2 points here, x1 and x2 on the anti-diagonal. So this is a period 2 orbit. And if we join the origin, which is a fixed point, with the point x1 using a straight segment, and we make the same here with the origin and the point x2, well, the images of these segments by the matrix A are these dashed lines here, okay, connecting 0 with x2 and 0 with x1. And this encloses a polygon. Well, so put this mesh here in dimension 3 inside the suspension of A, suspension flow generated by A. We will construct a surface in the following way. Consider this shaded horizontal part, which is the complement of the the polygon, and we can showing this segment here, the segment connecting 0 with x1. We iterate with the flow, and this defines a bond immersed in the manifold that goes here and comes back on this side of the figure. Okay, so we add this bond to the figure and we can make the same with the other segment. Well, the surface described like this, it can be seen that it is the embedding of a genus 1 surface on this three manifold. It is not a Birkhoff section like this because it is transverse to the flow in some parts, but it is tangent to the flow along these bonds, but it can be perturbed with some small isotopy and transform into a Birkhoff section. So it can be seen that this figure gives rise to a Birkhoff section. It is a genus 1 Birkhoff section with two boundary components, and it is possible to calculate the first return map here, which is given by the matrix 0, 1, minus 1, 4. Consider now the case of a suspension Anosov flow with some Birkhoff section sigma. So here we have a picture of a global transfer section T2 times 0 that we have shaded in green, and in gray we have a picture of what's the Birkhoff section. Well, this is not the Birkhoff section, but this is the blow down of the Birkhoff section. So the embedding here is obtained by blowing up these points, this finite set of points here, and then embedding the surface in the three manifold. So given any point on the interior of the Birkhoff section, there is some time, some future time or some past time that this point will hit the interior of the global transverse section and reciprocally. So consider one of these points and some intersection, not necessarily the first intersection, but some intersection with the other surface, and by the continuity of the flow, this produces a local projection of a neighborhood of the first point here onto a neighborhood of the second point. In other words, this construction allows to put charts, if you want, from the interior of the Birkhoff section into the global transverse section. So given some neighborhood here in the global transverse section, then we put it inside the three manifold, we project along the flow lines, and then we pull it back to the interior of sigma. And observe that the difference between two of these charts are necessarily given by iterations of the first return map onto the surface sigma. In the neighborhood of a boundary component, the picture is like this one. So here we have a tubular neighborhood of a periodic orbit that is a boundary component of the Birkhoff section, and here we have the embedding of the Birkhoff section and the embedding of the global transverse section. It intersects the tubular neighborhood in a disk and the other one in some kind of helicoid. Well, so this helicoidal-like surface is constructed as well, starting with some disk, but we have to blow up some point, then we obtain an annulus, and then we have to immerse this in the three-dimensional manifold. Well, the projections along the flow, in this case, if we start with some closed curve here in the disk, then we lift it to the annulus, and then we put it on this tubular neighborhood. Well, when we project this along flow lines, we cannot project continuously along flow lines, this curve, onto the transverse section, but this will project into a non-closed curve like this one, which starts in some point x and finishes in some power of the first return map to the disk here. Okay, so this is the point p power m pd power m of x. Now, the projections along the flow from a Birkhoff section onto a global transfer section in a suspension, they allow to endow the global section with some kind of affine structure but with singularities. Well, this construction that uh, I have seen it in some works of Thierry Barbeau and also Bonatti and Gelman. It's not exactly this construction, but it can be deduced from these from works of these people. Well, so consider some genus 1 Birkhoff section in a suspension Anosov flow, and the first return map onto the Birkhoff section is given by some hyperbolic matrix that we call it B. Well, consider the universal cover of this torus and the lift of the matrix here to R2. This provides an atlas of charts from small neighborhoods on the plane onto the Birkhoff section. And now we will consider the global transverse section here in green, and let's say that delta is the intersection of the boundary of the Birkhoff section with the global transverse section. So this is a finite set of periodic orbits like these points here. And for any small neighborhood in the complement of delta, well, by projecting this neighborhood along flow lines onto the Birkhoff sections and then pulling back with the universal cover, we can define an atlas here in the complement of delta. And this atlas satisfies the following. The change of coordinates are contained in this group, the group that is generated by the two integral translations, horizontal and vertical, and also by the matrix B. But if we take some closed curve here around some point in delta, and we lift this curve to the Birkhoff section and then to the plane, we do not obtain a closed curve, we obtain a curve with some holonomy. Well, so the holonomy must be given, or it's given, sorry, by an affine transformation of this form, where mi is the multiplicity of the Birkhoff section along this periodic orbit. And observe that the map FA here on the global transfer section, the map FA, if we choose charts of the atlas to parameterize some point, a neighborhood of some point and its image, then in local coordinates, this map is of this form. So here we have another picture of what this singular affine structure atlas is. We have the two-dimensional torus T2 with the action of the matrix A. We have a finite set of periodic orbits xi, xg, xk, and the atlas, it is defined in the complement of this finite set. Given some neighborhood, the change of coordinates between these two neighborhoods, it lives in this group gamma b, this group that we have called gamma b. So the transformation is like this one. If we look at the holonomy around some of these points, around the point xi, for example, when we make the holonomy development on the plane, we obtain a curve such that the beginning of the curve and the end are related in this way. And so here mi is the multiplicity of the Birkhoff section around the corresponding orbit. And finally, the map FA, the map that takes, for example, this neighborhood here onto this neighborhood, if we look at this map on the local coordinates provided by the atlas, well, this is also a transformation on the group gamma B. Now, the theorem that we want to present is this theorem. It says that there exists a natural bisection between the set of genus 1 Birkhoff sections for a suspension flow phi TAMA and the set of singular affine structures associated with the pair FA on T2 as before. So we have explained how a Birkhoff section induce one of these structures. So one Birkhoff section, one genus, one Birkhoff sections will induce one of these atlas on the surface. But we claim that for any given singular affine structures, like this one, we can find a Birkhoff section. And so the proof of this goes along the following lines. Consider the torus T2 endowed with a linear Anosov automorphism FA, and consider some sigma B atlas associated with this pair and with some singular set. So here B, remember that B is some hyperbolic matrix not necessarily equal to A. Well, so first of all, consider the suspension flow associated with A and make field surgery along the orbits corresponding to this singular set, but with twist parameter minus mi. What's mi? Mi here is the holonomy of the structure along the singularity xi. So make here a field surgery of twist parameter minus mi. for any of the periodic orbits. And in this way, we obtain a new Anosov flow that we call CT, sorry. Well, this flow is also endowed with a genus 1 Birkhoff section, that is the result of taking the global transverse section here and transform it with the Fried surgery. So that's um, a genus 1 Birkhoff section. And so we can project this atlas, this transverse structure, we can project this structure here onto transverse disks for the flow CTN. So the point here is that making this projection well along the singular periodic orbits, the locus of the surgery, the original structure it has had a holonomy of ME. Let's say the holonomy was determined by this integer MI. And since we have made surgeries with parameter minus mi, then when we project the structure in a transverse disk in a neighborhood of the singular, each singular orbit here, well, we obtain a transverse affine structure with no singularities. It has no singularities, the structure corresponding with this flow. So now, just apply the theorem of Plant and Bachbo to conclude that there exists a global transverse section that we call sigma b for the flow CTN. There is this flow, it is a suspension Anosov flow. It has a transverse affine atlas with no singularities, and it has a global transverse section that we call sigma b. And now, making surgeries back to M, we obtain in this way the desired Birkhoff section corresponding to the original affine structure that we have chosen. Now, to finish, recall the motivating question that we asked on the first part. When does a Birkhoff section come from a suspension Anosov flow? So the problem is given some Birkhoff section, not necessarily of genus 1, some Birkhoff section for some Anosov flow. We want to understand if this section comes from a suspension flow. So if this is the case, like in this figure, we have represented this situation in this figure here. Well, in the previous part, we have projected some atlas defined in the section onto the global transverse section, and we have obtained an atlas here. But we can do the process on the inverse sense. I mean, we can take the translation structure defined in this global transverse section and project it onto the Birkhoff section. And in this way, we obtain an atlas here, an atlas for this surface. And this atlas is related with the pseudo-Anosov first return. So in fact, the existence of one of these atlas in the Birkhoff section is enough to guarantee that it comes from some suspension. That we have to write the conditions. So the good conditions are this one. We have to find a sigma b atlas associated to this surface sigma defined in the complement of this finite set of points with change of coordinates in the group gamma b that we defined before. first of all, and second, the holonomies around each singularity xi. Now the singularity, it lives on the blowdown of the Birkhoff section, and when we make the developing map of some closed curve here around the singularity, so we must obtain a curve like this one. This curve has an holonomy defect between the starting and the ending point given by some power of the matrix B, and the power is determined by the multiplicity of these singularities. But also we will require that the curve winds n times around this singular point, where n, e are the linking numbers defined here. So this is the condition on the holonomies. And of course, we must require that in local coordinates, the map F is written as some transformation of this kind. Okay, so in this case, we can say that the flow VTM is a suspension Anosov flow. And the proof, up to all the combinatorics that is involved in this, it consists just in project transversely this structure defined on the Birkhoff section. We project onto transverse this in the manifold, and we obtain an affine structure without singularities, and then by Planck-Barbault theorem we can conclude that this is a